Okay, this video is a little bit different. I recognize that the major challenge of the homework set for the section on strategies of integration is that you encounter one of many types of integrals and you have to pick from many strategies. And sometimes you sort of hit a wall or you just have a block. You're like, I don't even know how to attempt this. The general advice is just try something. Just try some integration. You might screw up 3 or 4 times before you land on something. You might have to get a little bit creative. But don't feel like you have to see each strategy right away. With that being said, this video is full of spoilers on the exercises in that homework set. If you're completely stuck, you can sift through this video and look for some ideas on what kinds of strategies work. So I'm not going to be actually computing any of these integrals. I'm just going to be discussing how I would do them. So here is the first exercise in that problem set. And for me, actually, without even manipulating this much, I can tell right away that this really should be a trig sub type integral. And the reason is I see a 1 plus x squared, which is just like 1 squared plus x squared, right? That's the kind of expression that we should be looking for when we're thinking about trig sub. Also, another argument why I would try trig sub first is I can tell right away that regular substitution would not work. And the reason is if I were to substitute 1 plus x squared for u, then du would be 2x dx, and there are no x's upstairs here. So a regular substitution is not going to work at all. Checking in the book, I can tell that 1 squared plus x squared, that goes with the substitution x equals 1 tan theta, and the identity that you'll wind up using is tan squared theta plus 1 equals secant squared theta, and I believe that will get you to the correct answer. Here's another exercise in that problem set. This one kind of worried me for a little bit. I wasn't sure what to do with this guy, and I'm thinking that it's definitely not a trig sub, it's definitely not partial fractions, and I'm thinking that probably by parts or substitution are my best bets here. I'm not sure how the by parts went. I chose to attempt substitution first. I wonder if you could make it work with by parts. I'd be very curious if you did. I tried a substitution where u is equal to radical t, and that means that du is equal to 1 over 2 radical t times dt. I'm going to use the little trick where I'm actually going to solve for dt in terms of u and du. So dt is actually equal to 2 radical t du, but I think the radical t is stupid, so I'm going to substitute another u in there. Okay? And actually that turns this integral into the integral of 2u times e to the u du, and boom, I can tell that that looks like a by parts integral. So it's actually like a longer problem. You actually have to use 2 different strategies to get to the end of this exercise. This one is a little more obvious to me, I think, as someone who's done calculus a few times. The reason I say that is because I see the x and the ln x product, and that immediately triggers in my mind that this is a by parts integral. The ln x is something that I know the derivative of. That's easier. So I think that u should be ln x and dv should be x dx. And I bet you in one straight shot that'll get you to the end of that problem. This guy, on the other hand, looks a little bit trickier to me. Fancy e to the x expressions on the bottom. It's not like I can do a little algebra to break that up in any way. I'm not sure what to do with that. I don't see any way that by parts is going to work right away. Trig sub, obviously there's no like a squared plus x squared type expression, so I don't think that's going to happen. Partial fraction decomposition, it's not really a rational function. So should I try a sub? We could try a substitution. We could try u equals e to the x, and then du is equal to e to the x dx. And what that's going to turn this integral into is actually 4 over u minus 1 over u. Can you see that? Because that's e to the minus x power, so that's 1 over u. And the dx is actually going to transform into 1 over u du. And that's because if I take this equation and divide by e to the x on both sides, that's what I get. If I like smoosh those things together with a little bit of algebra, I get the integral of 4 over u squared minus 1 du. And I'm thinking that's awesome because that very clearly looks like a partial fractions decomposition type integral to me. Here is the next guy in the problem set. I guess I don't even know what to say about this. This is easier than it looks to me because secant squared x is the derivative of tan x. So I can kind of tell that this is going to be a substitution type integral. And so what's actually going to happen here is you're going to substitute u equals tan x. But I'm kind of curious. I bet that if you were to actually break this up by this subtraction here, that I bet you might have an easier time. If you were to break it up into the integral of secant squared x dx, and then you have the integral of 2 secant squared x tan x dx, and do the substitution on the second guy, I bet you're going to have a better time. This guy looks super tough. You have a quadratic under a radical, under a constant. It's ugly. On top of that, don't be misled. I mean, this quadratic actually factors to x minus 6, I think. No, not x minus 6. It factors to x minus 7, x plus 1. And you start thinking maybe partial fraction decomposition is the way to go here. But I don't think that's going to work because of the radical. So what's going to happen here is substitution is not going to work because there's no x's on top. You can't substitute u equals x squared minus 6x minus 7. Partial fractions won't work. Maybe we could try trig substitution because remember in that section we had a whole bunch of integrals where there was an a squared minus x squared under a radical. Fine, we can try this, but we have to complete the square first to make that expression look right. Factoring it in this way is not going to cut it. It has to look like exactly the right form. This is what that looks like. I'll get you started. You have x squared minus 6x minus 7, and that's going to be equal to x squared minus 6x plus 9 minus 16. And just so you know, how did I know to do that? I know that if this x squared minus 6x, if that were going to be equal to x minus something squared, it has to be 6 over 2. So I knew it was going to have to be x minus 3 squared. So I wanted this to have a plus 9. So I knew I had to write that. And then I'm like, well, what do I got to correct with? 9 minus 16 is equal to negative 7. It's an unusual way to complete the square, but that's my thought process. Anyway, this collapses in a gorgeous way to x minus 3 squared minus 4 squared. And if you replace this quadratic with this expression, now you are in a position to do trig sub, and you will be all set. Here is an integral that is full of trigonometric functions. And the first thing I want to say is don't forget that this plus means that you are allowed to consider these two parts of your integral completely separately. You do not have to think of them as one lump. And the integral of cos theta is a complete joke. You know what that antiderivative is. So it's like, all right, this guy totally easy, don't need to worry about that. That leaves the integral of cos cubed theta. Now that was something from the trig integral section where you learned how to deal with powers of trig functions. And this is a, quote, easier one where you have an odd power of cos. And what you're supposed to do is you're supposed to take that cos cubed theta and you split it into cos theta times cos squared theta. You split off one power of that cos. And then you take this cos squared theta and you rewrite it as cos theta times 1 minus sine squared theta, using that identity that sine squared plus cos squared equals 1. And this is great because you will be able to use substitution to finish this integral. Now on this guy, another ugly integral with just e to the x's. I guess by parts doesn't look like it's going to work, trig sub doesn't look like it's going to work. And so once again, I think I'm going to try to substitute u equals e to the x so that du equals e to the x dx. And in this case, once I make that substitution, I'm going to get 1 plus 2u on top, and I'll have 1 minus u on the bottom. And then I have du over u in place of dx, right? I can solve for dx and make that substitution. And when I simplify that using algebra, I get 1 plus 2u on top, and I get u minus u squared on the bottom, and bam, partial fraction decomposition. That's going to get you there because u minus u squared, that factors into 2 linear factors. So I bet that guy's going to split up real nice. Finally, here is an integral 3 minus 2x to the negative 1/2 power dx. I confess, this one tricked me. I was sitting around trying to think of, I rewrote it this way with the radical on the bottom, and I was thinking, oh my gosh, do I need to find a way to like make it look like a quadratic for trig sub? Do I have to rationalize the radical and make it like so the radical's on the top? And no, it's actually much easier than it looks. If you were to try a simple substitution, you will be able to find this antiderivative. So I hope that these hints were helpful to you and that you were able to answer the questions based on them. Don't forget, you are always welcome to reach out to your instructor if you have further questions on these homework sets.